Imagine you leave Earth in a spaceship, traveling in a perfectly straight line through the void of space. You continue on this journey forever, never stopping, never changing direction. As the years turn into decades and decades into centuries, a fundamental question begins to haunt you. Will you ever reach the edge of the universe? Is that even physically possible? Is there truly an edge to existence itself? This question represents perhaps the hardest and most mind-blowing problem in all of astrophysics. When we think about what might happen on such an infinite journey, we can conceive of really three possible solutions. The first possibility is that you eventually reach some kind of boundary that loops back on itself, like traveling around a sphere. You would complete a circuit through space and eventually arrive back here at Earth, exactly where you started. The second possibility is that you could continue forever and ever through infinite space, never looping back, never encountering any boundary, just traveling through an endless cosmos that extends without limit in all directions. The third and most mind-blowing solution is that perhaps, after an unimaginable journey, you would eventually come across an actual edge of the universe, a barrier where all of space and time simply cease to exist. And if you did make it there, if you somehow reached that point, what would you actually see? What would be on the other side? This profound problem has stumped the greatest scientific minds for thousands of years. Ancient philosophers wrestled with it. Medieval scholars debated it. Modern physicists continue to grapple with it. Today, we are going to attempt to solve this mystery together by building our understanding from the ground up, piece by piece, until we arrive at an answer that cosmologists believe is correct. But first, let me ask you a question that you might have never even asked yourself, because the answer seems so obvious on the surface. Why is the sky dark at night? What causes that darkness we observe every evening? The obvious answer is straightforward. The sun isn't illuminating the surface of Earth at the location where you are standing, so you get to see the true darkness of space sprinkled with twinkling stars, distant planets, and far-off galaxies. The darkness is simply the absence of the sun's light. But think about it on a deeper level. Why is space actually dark? What's the real reason for this darkness we observe? Consider this thought experiment carefully. It's certainly true that not all of the night sky is dark, right? We can see bright stars scattered across the heavens, stars very similar to our own sun, faintly shining all around the sky in every direction we look. Space is full of these stars. There are billions upon billions of them. But here's the critical question. What if the universe were truly infinite? And what if it were also eternal, meaning it had no beginning and would have no end? If this were actually the case, then you should be able to look in any direction, and eventually, no matter which way you gaze, you should find a star or a galaxy. You would look up, and eventually along any line of sight, your vision would encounter a luminous object. This principle suggests that our night sky should be as bright as the surface of the sun itself. There should be no darkness at all. Every direction should be ablaze with light. But this is not what we see. This is not reality. The night sky is predominantly dark, with stars appearing as isolated points of light. Maybe this means the universe is not infinite after all. Maybe there really is some specific distance away from us where the stars and galaxies simply stop existing. Perhaps there is an actual edge of the universe, a boundary beyond which nothing exists. Well, not quite, not exactly. This apparent paradox is a very famous problem in astronomy and physics, known as Olbers Paradox, named after the German astronomer Heinrich Wilhelm Olbers, though the question was pondered by many before him. So what's the actual solution? Why doesn't the night sky look blindingly bright? Why do we experience this darkness? Well, to answer this question properly, we need to go back to the very beginning of everything. We need to understand the origin and nature of the universe itself. The best way we can approach this problem is to first try and figure out whether the universe is infinite or finite. Is there a limit to how far space extends? Approximately 13.8 billion years ago, the universe as you and I know it today began with what we call the Big Bang. At this precise moment in time, the universe was completely filled with matter, antimatter, and radiation all mixed together. It was extremely hot, incredibly dense, and rapidly expanding outward in all directions. This expansion has continued for billions of years, with space itself growing faster and faster until we reach today. The universe is still expanding right now, as we speak. When astronomers look out to distant galaxies, examining them through powerful telescopes, they notice something genuinely strange and unexpected. The further away a galaxy is from us, the faster it appears to be moving away from Earth. This recession velocity increases with distance. So what if we take this observation to its logical extreme? What if we look so far out into the universe that the galaxies are moving away from us faster than the speed of light? Now, this seems impossible at first. Nothing can move through space faster than the speed of light. We know this from Einstein's theory of relativity. This is one of the fundamental laws of physics. Light is the ultimate speed limit, but here's the crucial distinction. That rule doesn't stop space itself from expanding and behaving however it wants. The space between galaxies can expand faster than light because it's not something moving through space, it's the expansion of space itself. Because the expansion of the universe is uniform, meaning it happens at the same rate everywhere, this phenomenon occurs at the same distance everywhere around us. This boundary where galaxies recede faster than light is known as the Hubble Sphere. Currently, it's located 14.4 billion light-years away from us in every direction. That's an enormous distance, far greater than the 13.8 billion light-years light has traveled since the Big Bang, which might seem paradoxical until you remember that space itself has been expanding. And here's the amazing part that makes this even more interesting. Because of complex reasons relating to dark energy and the accelerating rate of expansion of the universe, the Hubble Sphere is still expanding. It continues to grow bigger every single day, and it has been growing like this for billions of years. This has profound implications for what we can observe. This means that if some galaxies outside the current Hubble Sphere have emitted light traveling toward us in the past, eventually, as the Hubble Sphere expands, it will grow big enough to include this light. At that point, the light begins its long journey toward Earth. After billions of additional years, we will finally get to see that light and observe those distant galaxies. If you think about it, that's genuinely amazing. We can potentially see galaxies moving away from us faster than the speed of light. This creates a sphere of space that's actually bigger than the Hubble Sphere itself, a region that we can still observe no matter how far away it is or how fast it's receding. This is known as the observable universe. The true cosmic limit for everything we can possibly ever learn about is approximately 93 billion light-years in diameter. The reason it can be this big despite our universe being just 13.8 billion years old is because of this cosmic expansion. Space has been stretching throughout the universe's entire history. This sphere contains everything we can possibly observe. No matter how hard we try or how amazing of a telescope we build, we will never ever see beyond this boundary. But here's the crucial point. That doesn't mean that this is where space actually ends. Quite the opposite is true. There is certainly much more universe existing outside of this observable boundary. We just can't see it from our location. The fact that the universe is expanding is actually the key we can use to solve Olbers Paradox from earlier. Consider this famous image from astronomy, the Hubble Deep Field, taken by the Hubble Space Telescope using an infrared camera. This image is one of the most important and interesting images in the entire history of astronomy. Over the course of just 10 days of observation, astronomers captured images of over 3,000 individual galaxies in just a tiny patch of sky. A patch so small it's barely visible to the human eye, yet it contains thousands of galaxies. As the universe expands, distant galaxies move away from us here on Earth. As they do this, the light they emit gets stretched out. The wavelengths get longer. The light is shifted toward the red end of the light spectrum. This is called redshift. The farther away galaxies are, the faster they move away from us, so the more redshifted their light becomes. This redshifting keeps going all the way until eventually the light they emit becomes so redshifted that it shifts entirely into the infrared spectrum. At this point, we can't see them anymore with our human eyes because our eyes simply can't detect infrared radiation. That's why the night sky appears dark to us. Much of the light from distant galaxies has been redshifted beyond what our eyes can detect. To go beyond the observable universe into the unknown and figure out which of the three possible solutions to what's at the edge of the universe is correct, we first need to understand the shape of the universe at large scales. At first glance, it's easy to suppose that the universe would simply assume the shape of a sphere. After all, if the Big Bang started at some singular point and expanded outward from there in all directions, then surely it would expand into a massive ball containing all the matter and energy of the universe. This makes intuitive sense, which is why many of the great philosophers throughout history, including Aristotle, Ptolemy, and Plato, all believed this to be the case. It's what your common sense tells you should be true. But our actual observations of the universe don't seem to agree with this intuitive model. And like many things in modern physics, we have Albert Einstein to thank for revolutionizing our understanding. His theory of general relativity completely changed how we think about the structure of the universe. General relativity tells us that space itself is not just some flat, rigid grid like a checkerboard. Rather, it's a curved fabric of spacetime where mass and energy necessarily warp and bend the fabric itself. You've probably seen demonstrations of this concept, perhaps using a rubber sheet or similar surface, showing how a heavy ball placed on the sheet causes it to curve and create a depression. Objects rolling nearby get pulled toward this depression, which is how we explain gravity and planetary motion. But this same fundamental truth applies to the overall shape of the universe at the largest scales as well. When we consider spacetime at cosmic scales, there are three primary geometric possibilities for how it could be structured. First, spacetime can be positively curved. In this case, the universe would be shaped something like a sphere, but in higher dimensions. Your three-dimensional brain can't truly visualize these higher dimensions, so for ease of understanding, we can just consider it as a regular sphere, similar to how we experience Earth. In this positively curved space, light traveling in straight parallel lines will eventually converge and meet. They curve toward each other just like lines of longitude on Earth all converge at the poles. Another option is that spacetime can be negatively curved. This would be something like a saddle shape, like the shape of a horse's saddle or a Pringles chip. In this case, those same parallel lines of light would diverge, moving away from each other over time, spreading apart rather than converging. They would never meet. Or finally, spacetime can be completely flat. It would be neither negatively nor positively curved at the largest scales. In this case, the parallel lines of light will stay parallel for eternity, never converging, never diverging, just maintaining their separation forever. It's really easy to see how in the first positively curved solution, the universe could be seen as both infinite and closed. It would essentially be like the entire universe existing on the outside of a sphere, very similar to how we exist here on Earth. You could fly your spaceship around the outside of this spherical universe, traveling forever, eventually arriving back exactly where you started, just as you could travel around Earth and return to your starting point. But the spherical universe would have no boundary, no edge, just like Earth has no edge. It's not quite as easy to imagine how this geometry would work for the other two solutions. In the flat universe, the universe would just extend out infinitely forever, never repeating back on itself, never encountering any boundary at all. Space would just keep going and going without limit. Or perhaps the universe really does form this strange saddle shape, a hyperbolic geometry extending infinitely in all directions. So which of these three scenarios is it? How do we determine the actual shape of our universe? Cosmologists have measured the curvature of spacetime in our universe using a clever technique involving triangles and the cosmic microwave background radiation. In positively curved space, the three angles inside a triangle would add up to be greater than 180 degrees. In negatively curved space, these same angles will add up to be less than 180 degrees. And of course, in a flat universe, they would add up to be exactly 180 degrees, just like the geometry we learned in high school. By looking at the cosmic microwave background, which is essentially a snapshot of the light left over after the Big Bang, a radiation from the earliest period of the universe's existence, cosmologists can measure these angles for our actual universe. They can look at patterns in this ancient radiation and determine whether space is positively curved, negatively curved, or flat. You've made it through the hard conceptual stuff. You now understand that spacetime appears to be flat at the very largest scales. But what can this tell us about the true shape of the universe? What does flatness mean for whether the universe has an edge? Well, if our flat universe is finite, it could be that our observable universe is just a tiny, infinitesimal section on a more massive curved surface. This could be something like a hypersphere universe, a four-dimensional sphere embedded in five-dimensional space. It would be really quite similar to how here on Earth our experience feels like the Earth is flat, because we are just so incredibly small compared to the actual size of the Earth. You're standing on a sphere, but it feels flat to you locally. Similarly, the observable universe might only occupy a tiny section of a broader universe, such that it appears to be flat to us. This version of a finite universe would have to be at least 1,000 times larger than our observable universe to be consistent with our observations. But what if the universe is just truly infinite? What if it extends forever without limit in all directions? This is what most cosmologists believe today, and it has some genuinely scary implications for humanity's future. In this truly infinite universe, if it stopped expanding, you could fly your spaceship in one direction forever and ever without ever reaching an edge or looping back around to find the Earth. You would travel for eternity in one direction and never encounter a boundary. You would just keep going through infinite space forever. And here's where these scary problems come from. Here's where things get unsettling. If the universe is truly infinite, then everything in theory could repeat. There could be infinite copies of Earth scattered throughout space, with slight variations infinitely far away. Maybe out there in the universe, there really is a version of you watching this very YouTube video. But here's the thing, that version of you decides to not subscribe to this channel, while this version of you right now is choosing to subscribe. Both versions exist. This seems like complete science fiction. It probably doesn't sit right with you intuitively. It sounds impossible and absurd. But this cosmological model of an infinite universe actually predicts this as physical reality. According to the math and the statistics, exact copies of you and every other variation that you can possibly think of should literally live in a galaxy located 10 to the power of 10 to the power of 29 meters away from us right now. That is the number 10 followed by 100 billion trillion zeros. It's effectively infinity. It's such a large number that it's essentially meaningless to human comprehension. Now, theoretically, if the universe stopped expanding right now, you could reach these copies. If physics allowed faster-than-light travel and the expansion stopped, you could theoretically make the journey. And if you think about it really deeply, it actually kind of makes sense when you consider it logically. Everything here on Earth is made of a finite amount of particles arranged in a finite number of ways. These particles follow certain rules and laws of physics. If we have infinite space that is completely filled with galaxies just like ours in all directions, then statistics and probability say there must be repeats. These repeats could genuinely be anything. Maybe out there in the universe, somewhere there's a version where you are teaching me this topic through your own YouTube video. Who knows? The possibilities are literally infinite. But here's the crucial problem. Even if there are infinite versions of you out there somewhere in the universe, we will never reach them. And not because our spaceships just won't be fast enough, though that's part of it. More specifically, the laws of physics have locked us into this tiny section of the larger universe. The very structure of spacetime prevents us from traveling to these other regions. Do you remember the Hubble Sphere that we discussed earlier? Everything beyond this boundary is traveling away from us faster than the speed of light. The escape velocity, so to speak, exceeds the speed of light. This means that if we could somehow make a spaceship that traveled really close to the speed of light, we would still never catch up to them. We would always be too slow. We could accelerate closer and closer to light speed, but we still couldn't escape the expansion of space. Here's something that will make you think about the vastness of this problem. 94% of all the galaxies we can currently see are beyond this boundary, beyond the Hubble Sphere. They're already receding from us faster than light speed. This means that no matter how hard we try, if there are aliens living in those galaxies, we will never get to meet them. We will never be able to establish communication. We will never travel there. It's physically impossible within the laws of physics. And the situation gets worse. The number of places we can visit in our universe is just going to keep going down every single second. With each passing moment, the Hubble Sphere expands, but galaxies move away from us faster. The accessible universe shrinks. Currently, 60,000 stars pass beyond this horizon, becoming permanently unreachable by humanity every single day. That is more than 50 million stars that have become unreachable since the start of this YouTube video, in just a few minutes of time. Think about the long-term future. 100 billion years from now, every single galaxy will be too far away from us to ever reach. The light from those galaxies will be too redshifted for us to detect. In 2 trillion years, all of the galaxies will be so far away that we can no longer see them at all with any telescope. The universe as we know it, all the beautiful galaxies, nebulae, and star clusters, all of it will slowly fade out of view beyond an event horizon, almost as if it were entering a black hole. No matter how amazing a telescope we manage to build in the future, no matter how much technology advances, we will point it in every direction and always find the same thing. Silence and darkness, just empty space, for the rest of eternity. This has profound implications for the future of intelligent life in the universe. This means that if humans or any intelligent species evolved on a planet similar to Earth 2 trillion years from now, they would have never ever discovered galaxies. To them, the universe would be just their home galaxy and nothing else. They would have no knowledge of the Big Bang. They would never learn about galaxy formation. They'd never observe the cosmic microwave background radiation. They would probably believe that the universe is just static and eternal, unchanging and infinite, but dark and empty. They would have absolutely no way to discover anything we know today about the universe's history and structure. The evidence would be gone. The universe would have changed so fundamentally that the past would be erased from observation. It would be like we were living in a completely different cosmos than they would be living in. While this future scenario sounds depressing, it's not really as bad as it might seem. The galaxy does have more than enough space for humanity to thrive within. We have countless star systems, countless planets, infinite possibilities for exploration and colonization within our own galactic neighborhood. We still have no clue how to leave our own solar system and visit other stars. Alpha Centauri is only 4.4 light years away, and we still can't reach it with our current technology. And that's just the nearest star system. The galaxy is incomprehensibly vast. Regardless of all of that cosmic perspective, if you've made it this far in understanding this material, you now understand the true scale, size, and shape of the universe better than any astronomer or cosmologist did just 100 years ago. You understand the implications of an expanding cosmos. You understand the geometry of spacetime. You should be genuinely proud of yourself. You can now go tell all of your friends that we probably live in an infinite, flat universe with no edge. We can explain why the night sky is dark despite having so many stars. We understand our cosmic context. But don't get too comfortable thinking you now have all the answers. Humanity will continue to explore and discover the secrets of the cosmos for billions of years into the future. Who knows what we'll learn? I'm sure that by then, or even just 50 years from now, cosmologists will look back at this video in awe of just how little we really did know about the shape and size of the universe we call home. Science advances, understanding deepens, and the mysteries of existence continue to unfold before us.